So going back to the trope about IP version 4 being exhausted and there's too many users. So let's talk about some of the mitigations we've already covered. We had classes of IP addresses that were made into groups so that they were more efficient in how they were handed out. But we started to exhaust them. So then they created private addressing, where we took a dedicated portion of the IP address range and told everybody, only use this for internal use. Don't use it to talk on the internet. That way, all of these other addresses can be strictly reserved for public communication. And that certainly saved a lot of waste in the IP address schema, but it still wasn't enough because at the same time, you had a bunch of internal devices that had private IP addresses, but they still needed to talk on the public internet. So what did we do? So when RFC 1918 came out, one of the early solutions was network address translation. So network address translation utilizes a router as a boundary in the network to correlate the communication requests from an internal private address and then replace that address on the packet with a public address that router manages so that it can send that communication on the internet. So one thing to consider here, let's go back to the early days of the internet when everybody had a public IP address. There was no private IP addresses. So imagine there's a big business with a data center, and let's say they have 1,000 computers that are on their network that need IP addresses because they do IP-based communications. Well, because private addressing didn't exist, every one of those devices needed a public IP, even if they only talked internally in the network. They never talked on the internet, but there was only one type of IP address, public. So that was a huge waste. So when we went to this private address, that saved us a lot, but there were still some devices that even though they liked using the private IP addresses for private communications, some still needed to talk on the internet. So what happens when you have multiple computers that need to talk over the internet? Well, the solution with network address translation was a one-to-one approach, meaning, hey, before you were using 1,000 public IP addresses, and now you're only using 10 public IP addresses because you only have 10 internal computers that talk on the public internet. So, wow, we've saved a whole lot of public IP addresses. But the problem was, as computing advanced, as more computers gained more communications capabilities and we wanted to talk over networks that were further away, the reality was that, hey, now, all of these computers that were previously using private addressing, they're just putting more public addresses on these routers, and they're doing this one-to-one relationship. So as more private computers need to talk on the internet, they needed an additional public IP. So another way to look at it is, for every private computer that wants to talk on the internet, you needed a corresponding public IP. So for a while there, it slowed down the exhaustion of public IPs, but then as the internet grew and more devices wanted to communicate over the internet, well, we started burning IPs almost at double the rate. So we needed a new solution to stop the use of this one-to-one relationship, one public for every private address that needed to communicate out on the internet. So the solution to the NAT problem, as more devices started to communicate on the internet, was port address translation. So we're going to learn more about ports later, but just for right now, a port is a logical number that is used to associate a known service. Meaning, if you want to talk to a web server uses a well-known port that any network communication service would recognize. So it knows if I'm talking to a network service over a well-known port, I know what type of communication I'm going to be doing. Oh, I'm talking to a web server. I'm going to send it web server protocols to talk to it appropriately. So the benefit of PAT, or port address translation, in conjunction with NAT, remember NAT is this approach where we have a public IP for every private IP address, but that doesn't scale because we have more private addresses wanting to get on the internet now, and we're already running out of public IP address space. So PAT was an addition to the NAT address table where we would say, hey, let's keep track of our private sessions inside of our network that are trying to talk out, and then do a reference to the session on the public side, meaning we can use one public address for multiple private addresses internally to our network. That way, we didn't need to have a bunch of public addresses. We can get away with one public address and multiple private addresses. And this is what's happening for your devices at home right now. Your ISP is giving you one public IP address, and you have multiple devices inside your network that are talking on the internet, and it's because NAT, which is correlating your private address to a public address, but then the addition of PAT, which correlates the unique ports your internal session is using, and it corroborates that or matches it to a public session. That way, we can use all of these different sessions over one IP address, and the router can manage all of these unique sessions instead of having to give you your own IP address. So let's look at NAT and PAT in action. Hopefully this makes a little bit more sense. On the right end of this diagram, we have 3 hosts with the IP addresses 10.0.0.5, 10.0.0.18, and 10.0.0.23. If we didn't have PAT, we'd have to have a public IP address for each one of these private hosts that want to talk on the internet. But again, there's not enough public addressing anymore. So what happens is when each one of these hosts A, B, or C, want to talk to the internet, they establish a normal session. Hey, I want to go to gmail.com. Gmail's IP is this. I'm going to, build my IP header, and I'm going to send that through my switch, which is going to send it to the router. And hopefully we're off to the races and out to the internet. But the router says, hold up, I've only got one IP address. So I have to modify your header and change some values. So what it has is this internal NAT-PAT table. And we can see on this table on the right, we have internal sessions. So these are active sessions. And we can see our internal IP addresses, those IPs ending in 5, 23, and 18. And they're using an internal host port. We can see just next to them, 65.430 for the .5 address, 5873 for the .23, and 5561 for .18. These ports are what are referred to as ephemeral or high-ordered random ports. They don't mean anything. They're not tied to a specific service. They're just randomly used by computers and picked randomly. And then we can see we have this PAT port. That is the port that the router is going to use to communicate on the external side. So what it's able to do is it changes your internal IP in the packet header with its public IP, and it changes your private internal port, your source port, with its source port, the router's source port that it's going to use to talk to the internet in that service. And that way, from the internet's perspective, it looks like we're just talking to one IP over a bunch of different ports. We have a bunch of sessions with a bunch of ports from one IP, when in reality, those sessions are denoted by the ports. And each of those sessions belong to a unique internal private host. So internally in the network, if we were monitoring, we'd be able to see all of these private communications. We would see host A is using port 65.430 because we're before the NAT if we're inside the network, right? So we see all the traffic before it's translated. So we would see all the unique hosts making these unique requests. However, if we collected or monitored the network outside of the router on the internet side of things, we would only see the one public IP that router manages, but we would just see a whole lot of sessions with unique ports. We don't know if those sessions belong to one computer or many computers. But if we were on the inside again, we would know for a fact which sessions belong to what host. And that's essentially what happens here. NAT is a one-to-one relationship from a private IP to a public IP, and PAT, port address translation, allows us to monitor unique sessions using ports so that we can have multiple sessions for one public IP to many private hosts. That way, we reduce the amount of public IPs we needed for a network to communicate while also still making efficient use of our private addressing space that was given out to us. So before we wrap up this lecture, let's talk about the other main internet protocol that's in use, IPv6. And like I said previously, IPv6 is newer. It's been around for about 10 years, and it's simply not been adopted because one of the major issues is that some devices, I would say, probably more devices now support it than even 5 years ago. But a big problem is there's many devices on the internet that simply do not support IPv6 because IPv6 has a completely different protocol header. It is a different size source addressing. So you can see the problems with all of these legacy devices, routers, and things on the internet that simply don't support IPv6, and that being a problem. So IPv6 is a 128-bit string. Remember, IPv4 was only 32, so just off the bat there, we realize we're dealing with a way bigger number. But what makes it even more computationally larger is the fact that it is hexadecimal. Instead of binary, we're working with hexadecimal values, which are represented in the characters A through F and 0 through 9. So if we look at the total number of addresses for IP version 6, it would be 2 to the 128th, or 340 undecillion. That is 27 zeros past 999 billion. And remember, this is a ridiculous number for the fact that they thought IP version 4 with 4.29 billion addresses was a ridiculous number. The creators of the internet never thought in their wildest dreams, and even in their lifetimes, that they would see the exhaustion of 4.29 billion addresses. And that's just a testament to how pivotal and pervasive the internet is in our modern lives. But we can all agree that this is borderline just egregious with IP version 6. 340 undecillion, I never even knew that was a number until I learned about IP version 6. And a way it's been characterized is there's more IP version 6 addresses than there are grains of sand on the earth. Or we have enough IP version 6 addresses to give each cell in your body its own IP version 4 equivalently sized internet. Let that sink in. Every cell in your body can get like 4.29 billion addresses, and we'd still have enough left over. So let's look at the format of IP version 6. So in base 2, we have those 128 ones and zeros, so considerably longer than an IP version 4 that we saw. And then we have a base 16 or hexadecimal representation of that address. And even though that's a lot shorter, that's still much harder to remember than an IP version 4 address. I think that's one of the biggest things IP version 4 has going for it, is it's relatively easy to remember, oh, my IP address is 10.53.128.10 versus 2001.000.3238 DFE1 and so forth, right? That's sort of hard to remember that long string. And for that and a lot of other reasons, I think we're going to see a lot of IP version 4 in private networks for a long time, simply for the fact that we can have a class A address, 16 million IPs, inside of our private network. Why change? They're much shorter, they're easier to read, and there really isn't a whole lot of value or advantages to them right now. IP version 6 does support more advanced communications, but the internet and those communication services haven't picked up pace to make them really mainstream yet. So one thing to know about an IP version 6 address that makes it a little bit easier to manage is that we can remove repeated zeros or repetitive zeros. You can't remove any zero if there's a number preceding it, right? Because remember, it's binary, so you can't start with a 1 and then have trailing zeros and remove those zeros. You've effectively changed the whole value of that number. But when we have a section that's all zeros, you can easily change it to 1 0, or you can just actually remove the 0 entirely and just leave a colon there. The computer knows that if there's no 0 there, the default is 0. So you can shorthand these addresses somewhat. What's a little bit different about IP version 4 versus IP version 6 is that IP version 6 is so large, we don't really deal with classes or public versus private. The first 64 bits of an IP version 6 address define the network as well as the subnet ID. We have subnet IDs baked right into the address. So no more subnetting, no more classes or ranges of addresses to really deal with. And the last 64 bits deal with the host. That's the host portion of the addressing schema. So we have some similarities between IP version 4 and IP version 6 from a unicast, anycast, and multicast. We can see that we've lost broadcast, and we now have this anycast address. So let's go through these really quick. Unicast, just like IP version 4, was for single interfaced host-to-host communications. My computer wants to talk to another computer. So IP version 4 had unicast, and so does IP version 6. Nothing's changed there. But we've lost broadcast address, where we want to broadcast devices on our network where everybody's going to listen. What we now have is anycast addresses. And what they're able to do is they are able to be subscribed to one or more interfaces. And this is allowing devices to handle like services or functions over the internet. And the reason we went to an anycast address is because we have services that are virtualized, that are distributed, and handling processes over a distributed architecture. We no longer operate in a day where a server is just truly one computer standing alone by itself. Most modern web applications and services are a myriad of hosts offering features and functions over the network. So Anycast addressing allows us to share or provide those services over the network. And an example here is load balancing. We can have requests sent to multiple services that balance the load of those requests using an Anycast IPv6 addressing schema. And just like IPv4, we retained the multicast. And recall, multicast is where it's a type of broadcast, except instead of everybody mandatorily listening to that broadcast, only those subscribed to those messages will listen and respond. Here's an example of an Internet Protocol version 6 header. Somewhat similar, a few terms still match to an IPv4 header, but it's been simplified. We've gotten rid of a lot of header values that we dealt with in IPv4, but we can see overall the header length is considerably longer because those addressing schemas, we went from 32 bits to 128. So we have to take up 4 times the amount of space to quantify our source and destination addressing. So looking through this header, again, we have our version field like we did with IPv4. Next, we have the traffic class, which is similar to the type of service field we saw in the IPv4 header. It essentially provides processing priority precedence to how this packet should be received and handled by the device that receives this packet. And next we have flow label, and flow label is unique. It's something new, but it still has some bases in IPv4 or some legacy hardware. So if you remember from IPv4, we had fragment offset, and we had the ability to denote if packets were fragmented. Well, the flow label has some similarities in the sense that it allows devices to tag packets as being a part of a flow, but it's for optimization of streaming data. So as the internet has matured, we've consumed considerably more digital streaming media than we used to when IPv4 was defined and created. Remember, IPv4 was made in the 70s, and IPv6 is much newer, and it's taken into account the nature of how the internet operates today, and takes into account with how the internet operates today with more flowing, rich media, and we have to optimize and identify which packets belong to a specific flow or session. The next field we have is the payload length, which is quite obvious, is that it tells us the overall length of the payload attached to this header. So the next header field somewhat works in conjunction with the flow label. So remember, the flow label is how we can tag packets as being part of a flow for optimization of streaming media. The next header is an offset or notification that there's more headers coming that are associated to a potential flow or a packet session. So if it doesn't have a value, there's no subsequent header in this communication. It's to allow routers to better optimize resessionization of data and optimizing how we manage and prioritize these packets in a flow or session. Again, we have a hop limit, which is similar to the TTL. This ensures that the packet does not live on beyond a maximum number of routers that it's communicated with. So it'll be just dropped if it can't get to its final destination. And then last but not least, we have the 128 bits allocated for the source address and another 128 bits allocated for the destination address, followed up with that payload value, which was identified in the payload length. So in summary, let's talk about some key things it's important to remember. And one of the first ones being it's important to remember that private versus public address ranges. It's critical to understanding how subnetting creates and defines the size of a network. If you're doing triage on an IP address that's attacking your network, you want to be able to do research to correlate how big is the network that server or device is being hosted at. Are the other addresses from that network also to be considered malicious and non-trustworthy? So being able to scope networks appropriately ensures that you account for all the addresses in that bucket and no more, no less. NAT and PAT dictate what traffic looks like, and that's based on the perspective of where you monitor the network. One portion of network defense is obviously monitoring the network, and we have to pick where we collect data from. If we're collecting data upstream from a router, meaning after the NAT, we're only going to see that one public IP address or even a few public IP addresses that router manages. So we don't know if it's a few IPs with a lot of sessions, or is it a bunch of addresses with a few sessions? We don't know if it's one host back there or many behind that NAT device. So it changes dramatically what we're looking at if we collect upstream in front of that router or downstream inside the network, where we can now see all of those unique private IP addresses trying to talk out on the internet. And that drastically changes how we handle our alerts and we do our triage. And again, IP version 6 is the future protocol. It has more than enough addressing space to last us for quite some time, but it's not adopted as fast as people would have thought, simply for the fact that we have private addressing that works really well in our internal networks, and there's no fear of those addresses being lost. It's sort of a cat and mouse game. Vendors haven't replaced traditional IP version 4 because internal network users are still using it and there's really no problem. So if they mandate an IP version 6, you're essentially telling your customers to change all of your addressing schemas and setup inside your network, and nobody really wants to pull that trigger yet, right? So it's just going to be more of a natural adoption as IP version 4 truly becomes exhausted and there's literally no more addresses for people to use. They're going to have no choice but to use IP version 6, and that's how things are going to slowly switch over to fully IP version 6 public internet. But I personally think for a very long time, you're going to see IP version 6 RFC 1918 private communications long after we've switched to IP version 6 on public internet communications.